Welcome to this explainer. Have you ever actually looked down at a tiled bathroom floor, or maybe up at a brick wall, and wondered about the hidden mathematical laws dictating those patterns? Well, today, we're going to explore the absolutely fascinating world of plane tilings. We'll uncover how these incredibly strict geometric rules govern the visual order we see everywhere in our world. And, honestly, perhaps more excitingly, we're going to meet the mathematical rebels who completely shattered those rules. Let's just jump right in by looking at the physical world around us. Human beings and nature. We are both absolutely obsessed with repeating patterns. On the left side of your screen, you see a honeycomb, which is just a marvel of natural engineering. And on the right, a completely ordinary set of roof tiles. So what actually links a swarm of bees to human architecture? It all boils down to an innate drive toward efficiency and symmetry. These are prime examples of grounding abstract geometry right into everyday reality. They're essentially solutions to a very specific spatial problem. How do you cover a flat surface continuously without leaving any gaps? So, here's our roadmap for today. We're going to look at symmetry in the real world, the 17 wallpaper groups, the 3 magic tilings, the mathematical proof behind them, expanding with Archimedean tilings, and finally, breaking rules with aperiodic tilings. All right, part 1, symmetry in the real world, or the basic rules of visual order. Before we start categorizing all these rules, we kind of need a shared foundation. Like, mathematically speaking, what actually is a tiling? Basically, a tiling of the plane is just an arrangement of planar objects, we call them tiles, that covers an entire flat surface without any overlapping. And the rules of engagement here are pretty simple. Any two adjoining tiles have to either share a common corner, also known as a vertex, intersect perfectly along a pair of their edges, or just not touch at all. If you can take a shape or a set of shapes and repeat them infinitely across a flat surface following those exact rules, boom, you've got yourself a tiling. Moving on to part 2, these 17 wallpaper groups, where we talk about organizing infinity. So now that we know what a tiling is, let's step from the physical world into the realm of mathematical categorization. Just look at the sheer variety of patterns here. Now, unlike simpler frieze patterns that really only extend in one direction, wallpaper designs have translation symmetries along 2 non-parallel vectors. You can think of it kind of like a grid that's pulling the pattern left to right, but also up and down at the same time. Any translation symmetry of these objects is just a composition of translations along these 2 basic vectors. And here's the truly wild part. Mathematicians have actually proven that every single repeating 2D pattern in the universe falls into exactly one of these 17 types of symmetry groups. No exceptions. And this isn't just some abstract artistic exercise either. These wallpaper groups are directly connected to hard science. Mathematically, they're known as 2-dimensional crystallographic groups. A mathematician named Fedorov was actually the first to classify these 2-dimensional groups way back in 1885. And this classification is literally fundamental for crystallographers who study the atomic structure of crystals. So the exact same math that gets you a nice-looking bathroom floor is also helping scientists understand the molecular makeup of solid matter. Pretty cool, right? But what happens when we start restricting the rules? Which brings us to part 3, the 3 magic tilings, exploring the strict limits of regular polygons. Okay, we're going to talk about monohedral tilings now. That basically means attempting to cover a plane using only one single type of regular polygon of a fixed size. Now, out of literally an infinite number of possible regular polygons out there, how many do you think can perfectly tile a flat plane completely on their own? Get ready for this. Exactly 3. That's it. Just 3. So, here's the first of those 3 magic shapes, the equilateral triangle. If you look closely at any vertex, again, the corner where all the points meet, you'll see exactly 6 triangles coming together perfectly. There are 0 gaps and absolutely no overlap. And here are the other 2 shapes, beautifully illustrated. On the left, you've got the monohedral square tiling, where exactly 4 squares meet up at every vertex. And on the right, the monohedral hexagonal tiling, where 3 hexagons meet at every vertex. Triangles, squares, and hexagons. That is the whole list. But why? Why does the universe limit us to just these 3 regular shapes? Well, let's find out in part 4, the mathematical proof. Time to solve this geometric mystery. To definitively prove why the laws of 2D geometry put us in this box, we need to put on our detective hats for a second. Look at that crucial point right there in the dead center of the hexagon. For any tiling to lay completely flat without warping or, leaving weird empty spaces, the interior angles meeting at any given vertex must add up to a complete circle. They literally have to sum to exactly 360 degrees. If the sum is even a little less than 360, you get a gap. If it's more than 360, the tiles are going to overlap or buckle upwards. So, how does this translate into algebra? It's actually highly logical. Step 1, we establish that the interior angle of any regular polygon with m sides is 180 minus the fraction 360 over m. Step 2, if we have, say, n number of these polygons meeting at a single vertex, we just multiply that interior angle by m. And step 3, because they absolutely have to form a full circle, we take that entire equation and set it equal to exactly 360 degrees. And through a little bit of elegant algebraic simplification, that longer equation reduces down perfectly to this: m minus 2 times n minus 2 equals 4. This simple little equation is the exact culprit behind our limitation. Remember, m is the number of sides on the polygon, and n is the number of polygons meeting at the vertex. Both of those have to be positive integers. And the only positive integer factors of 4 are 1, 2, and 4. Because of this hard mathematical truth, m can only ever equal 3, 4, or 6. And that, my friends, is exactly why only triangles, squares, and hexagons can exist as regular monohedral tilings. Mystery solved. But of course, mathematicians rarely like to stop at boundaries, do they? Which leads us to part 5, expanding with Archimedean tilings, where we start mixing up the regular shapes. So let's see what happens when we keep the rule of using regular polygons, but we actually allow more than one type of shape to join the party. Enter the Archimedean tilings. By mixing different regular polygons, like combining triangles with hexagons, or maybe squares with octagons, as long as we ensure the pattern at every single vertex is completely identical throughout the entire tiling, we expand our possibilities. But even then, the rules are still pretty tight. There are exactly 11 Archimedean tilings. And what's kind of crazy is that this brilliant expansion of the geometric rules was originally discovered by the famous astronomer and mathematician Johannes Kepler way back in 1619. His findings were actually totally forgotten for like 300 years before somebody finally rediscovered them in the 20th century. All right, part 6, the finale. Breaking rules, aperiodic tilings, or finding order without translation. Now we pivot to the absolute climax of this whole explainer. Literally every tiling we've looked at so far has translational symmetry, meaning you can slide the pattern over and it perfectly matches back up with itself. They're periodic. But what if you wanted to tile a plane infinitely without ever repeating a translation? Well, enter the rule breakers. The hunt for aperiodic tilings, tilings with zero translational symmetries that can never ever be rearranged to be periodic, was honestly a massive mathematical drama. Back in 1961, a mathematician named Wang conjectured that any set of tiles that could cover a plane could always be arranged periodically. But then, in 1966, Berger completely shattered this idea. He successfully found an aperiodic tiling. The catch? He needed a mind-boggling 20,426 different types of tiles to pull it off. So the race was on to shrink that number. Over the years, mathematicians kept whittling it down until 1974, when Roger Penrose spectacularly achieved an infinite non-repeating pattern using, wait for it, just 2 tiles. I mean, just look at the genius of these rule-breaking designs. On the left, you've got Penrose's aperiodic tiling, and it uses just a kite shape and a dart shape. And what's wonderfully poetic here is that these 2 Penrose tiles are actually made by gluing together pairs of golden triangles, which are shapes derived from the famous golden ratio. And on the right, we've got Ammon's tiling, which is another aperiodic masterpiece that also just uses 2 tiles sharing golden proportions. These patterns create perfect order, they can cover an infinite plane forever, yet they never neatly repeat themselves through translation. It's literally organized chaos at its absolute finest. So as we wrap up this explainer, I really want to leave you with this one thought. We've journeyed from the predictable, everyday symmetry of honeycombs all the way to the rigid, algebraic laws of regular polygons, only to watch modern mathematicians find loopholes that create infinite, non-repeating beauty using just a couple of shapes. It kind of forces us to ask, if such complex, hidden geometries can be coaxed out of a simple, flat plane, what other mathematical secrets are just waiting out there to be discovered? The next time you walk across a tiled floor, take a closer look. You might just be stepping on a mathematical masterpiece.